Hi, I'm Joe James, and this video is going to cover binary search trees. So a tree is a collection of nodes with edges that connect them. The nodes are organized into levels, and the top level is called the root node. Each node can have child nodes. In this case, the 3 is a parent node, and it has a left child and a right child. And the left and right child are called siblings because they share the same parent. The 1, 4, 6, and 9 nodes here are called leaf nodes because they don't have any child nodes. In a binary tree, each node can have up to 2 child nodes, a left child and a right child. Node 5's right subtree includes everything in this triangle, which is a tree in itself under node 5. Node 5's left subtree includes nodes 3, 1, and 4. Node 4 has ancestors, which are simply every node between itself and the root node. And node 5 has descendants, but basically every node below it, all of its children node and their children's nodes, and so on. In a binary search tree, each node is greater than every node in its left subtree. So for example, 15 is greater than every node in the left subtree. Node 8 is greater than every node in its left subtree. Node 5 is greater than the 2 in its left subtree. Node 24 is greater than 19 in its left subtree, and so on. And each node is less than every node in its right subtree. So here we can see that node 15 is less than all the members of its right subtree. 24 is less than the members of its right subtree. 8 is less than the members of its right subtree, and so on. These two characteristics make a binary search tree. Binary search tree operations, we have insert, find, and delete. So for a binary search tree insertion, we start at the root, which is node 15. Let's say we want to insert a 12. We're always going to insert a node as a leaf. So our first comparison will compare 12 to 15. 12 is less than 15, we take the left child. We compare 12 to 8. 12 is greater than 8, so we take the right child. We compare 12 to 11. 12 is greater than 11, so we take the right child. We'll compare 12 to 13. 12 is less than 13. 13 has no children, so we add 12 as a new left child for node 13. So we can see that node 12 is inserted as a leaf node. For the binary search tree find operation, we also start at the root. Let's say we want to find node 19. Our first comparison is 19 less than 15. No, it is not, so we take the right subtree. Is 19 less than 24? Yes, it is, and there we found 19 already. So find operation is pretty simple. And the binary search tree delete operation, there are 3 possible cases. Either the node you want to delete is a leaf node, it has 1 child, or it has 2 children. And we'll look at each case separately. So first, let's say we want to delete a node that is a leaf node. Now in this tree, we can see that nodes 2, 6, 12, 19, and 25 are all leaf nodes. So if we want to delete one, we can simply delete it without affecting the rest of the tree. Now if we want to delete a node that has 1 child, and in our tree example here, we can see that nodes 11, 13, 28 all have 1 child. If we want to delete, for example, node 11, we can see that 11 is node 8's right child. So we make 11's only child, 13, 8's right child. In other words, 13 takes 11's place. And then we can delete node 11. Now note here that node 12 stays attached as 13's left child, and that does not change. It does move up a level in the tree, but it stays attached as 13's left child. So 13's subtree is not affected. Now if we want to do a delete operation with 2 children, let's say we want to delete node 24, which we can see has a left child and a right child. We find the next higher node. So we do that, we look at node 24, we follow the right subtree, node 28, and then we look at left child and left child, continue down the leftmost path until we get to the bottom. In this case, there's only 1 edge to node 25. So that is the next highest node from 24. So in this case, we can change the 24 to 25 and delete node 25. In the last case, let's say we want to delete a node that has 2 children, in this case node 4. So 4 has a left child and a right child. So first we're going to find the next higher node, which is 6. We change the 4 to a 6, and then we can delete node 6. And since the delete operation is done recursively, the 7 basically takes 6's place, and the 6 is gone. So the advantage of binary search trees? Speed. We can insert, delete, and find in big O of h speed, which is big O of the height of the tree. That means that in a balanced binary search tree, with 10 million nodes, find, insert, and delete operations take only on the order of 30 comparisons, which is incredibly fast. That wraps up our introduction to binary search trees. I'm Joe James. Thanks for watching.